This is a ratio. Take two numbers and you compare them to each other. Then when you get your ratio, if you compare it to another ratio and it turns out that they're equal to each other, that's called a proportion. There are some rules of proportions. All of these things say the same thing. If one of them is true, all of the others are true. And you could refer to it as rules of proportion if you like, or you could just look at it and say, all the regular rules of equations are the ones that would give you these different values or different expressions of the same proportion. That's important because the very first thing we did was talk about similar figures. And similar figures are figures that are the same shape, but not necessarily the same size. If I have two triangles that are similar, the way you write that two triangles are similar is with this symbol right here. And what this says is that triangle ABC is similar to triangle EDF. And you'll notice they're not oriented in the same way, but it doesn't matter. This tells you everything you need to know. This sentence right here includes these 6 facts. This angle is congruent to this angle. This angle here is congruent to this angle here. And this angle here is congruent to this angle here.
Bless you.
Okay, that's what this is. And also the sides, when you compare the corresponding sides of the two triangles, they have the same proportion. That's what it means for two triangles to be similar. If you're looking at a triangle, at a pair of triangles like this, and you want to compare the sides to see, do they have the same ratio? Which sides would you compare to which sides?
12 and 6, 9 and 17 and 15.
Okay. So you would take C and compare it to D. You said, what was the other one? 15 and 30?
Yeah.
Okay. So you would take B and compare it to F. And you would take A, I guess what's left is compare it to E. And you do that because you are comparing the largest one of these with the largest one of these, the smallest one of these with the smallest one of these, and the medium size to the medium size. And the truth is, it's close, but it's not going to be, because although this is twice as big as this, and this is twice as big as this is almost twice as big as that, but not quite. But the point here is you have no chance of finding ratios that work if you don't compare the big side to the big side, the little side to the little side, and the medium side to the medium side. Okay? That's the only chance you have of finding side ratios that will be equal. Now, just like when we were doing congruent triangles, you don't have to prove all of this to decide whether or not the two triangles are similar. There are 3 shortcuts. If you can show that two pairs of angles in the two triangles are congruent, that will work. If you can show that all 3 sides, all 3 pairs of sides, share the same ratio, that will be enough. Then you don't have to talk about the angles at all. Or if you can show that 2 sides, 2 pairs of sides, have the same ratio and the angle in between them on both triangles are congruent, that will be enough. These are the 3 ways of going about proving that triangles are similar. One of the things that happens after you discuss similarity, we took a look at right triangles. And we said, okay, this angle right here, we're going to give this a variable here and call this theta. And this is a right angle. And then I'm going to take another shot at this over here. Are these two triangles similar?
Yes.
By what?
Angle.
Angle. Exactly right. So if this is A, B, and C, and this is D and E, what would the triangle similarity statements be?
Triangle DAE is congruent to triangle.
Not congruent,
I mean,
similar.
to triangle BAC.
Okay. And that's because these two angles are congruent. They're both right angles, and right angles are all congruent to each other. And this angle here is shared by both triangles, and we call that the reflexive property. Everything is equal to itself. Okay? Yeah.
Are D and E parallel to B and C?
Well, what do you think?
Yes.
Why?
Because of what's it called? The corresponding angles are congruent.
Right. This is a transversal that crosses these two lines, and the corresponding angles are congruent, so that means the lines themselves have to be parallel. Okay? Now, what I want to do is look at this from here to here and call it C, from here to here and call it D, from here to here, call it B, from here to here, oh, actually this would be E over here, the big one. Over here would be D. Right? You see what I'm doing? I'm using the angles to talk about the sides across from them. This would be A1, this would be A2, because they're both across from angle A. So across from angle D on this triangle, I've got this long stick here that's D units long. Across from B, I have this that's B units long. Across from C, I have one that's C units long. I have across from E, one that's E units long. And across from A, I've got A1 and A2. And here's what we know about these sides. We know that the proportion of C to E is equal to the proportion of B to D, and that's equal to the proportion of A1 to A2.
How do you do it?
Because the two triangles are similar because of angle, and once we know they're similar, we know that the corresponding sides share the same ratio. Okay?
So once you prove it some way, you can like prove everything.
That's what makes it a shortcut, yeah. Right, and it's just like with congruency, if you remember when we showed that hypotenuse and leg were the same, that was enough, we didn't have to show any more. Okay? So the same thing is true here. Now, of course, if you think about this, anywhere I draw a right angle, here, 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 I'm going to be creating triangles that are all similar to each other and that all share this angle and all have right angles here and all have ratios that are equal to each other. Okay? Now, these particular ratios might not be the same. In other words, E might be twice as big as C, or it might be 3 times as big as, but the ratios among the triangles, right, C to B and C to A1, those are going to be the same. So that means that for every one of these triangles, right, this side here compared to this side here, let's just talk about one of them for a minute. We'll say B, actually let's say A1 over B is always going to be the same, right? This over this will be the same as this over this, will be the same as this over this. All of those ratios are the same, and so are the ratios that come from this over this, or this long one over this long one.
What's the ratio?
Those ratios will always be the same. Now, I'm using B over C as the, because I'm using this triangle as my example. But then also, A over C will also always be the same as long as it's a right triangle with that angle in it. That's part of similarity and the proportion rules. So that means that for any angle theta, I could make a list of these things. Now you'll notice that A over B is actually the slope of this line, rise over run. We call this the tangent of theta.
Which one is the tangent of theta? A1 over
Rise over run, right? Because it's the same as the slope. This one here we call the cosine of theta. And this one here we call the sine of theta. And I could be using things like, the side that's straight up and down, or the side that's flat, or rise and run. But what'll happen is we'll get triangles that go in every which way, and that's going to just be confusing. So instead what we do is we say, look, here's our reference angle. This is the angle we're using. This, of course, is the hypotenuse because it's across from the right angle. This one right here is opposite the angle that we're talking about. So we're going to call that the opposite side. This is the side that's right next to the angle we're talking about. We're going to call that the adjacent side. Okay. Again, the adjacent side over the hypotenuse. And then the opposite side over the hypotenuse. These three things will be true for every right triangle that has an angle with this measure in it. And if you look at this, you'll realize these are just three numbers. This is a number, this is a number, and this is a number. The only trick is for these numbers, we don't actually tell you exactly what they are. We tell you in code. So this is a number, but if this angle was 20 degrees, for example, I can't memorize all the different tangents of all the different angle measurements, but there's a code book, or in your calculator, a code breaker. So if you put in tangent of 20 degrees, it will tell you what that ratio is. That's a number. This is a number, and this is a number. That means for each one of these situations, these equations just look like this. Number equals number over number. And the truth is, if I give you two of these numbers, you know how to get the third one. Which means you can do the same here. If I give you two, you can give me the third. Now on this side, it requires coding or decoding tangent, cosine, sine. But that's not such a big deal. Yeah.
Could you go over how if you had in that equation BC, you'd find A? Like, if you had the B over C, you'd find A.
If I had B over C,
Yeah, they'd just have that unit.
B over C would be equal to A. Whatever the ratio is, I would divide C into B. That would equal A. Now, then I would have to figure out, depending on which one of these I was working with, I would have to go backwards in my chart, or I would have to use the inverse function on my calculator to figure out what the tangent, what this is the tangent of, so that I could get the angle measurement.
So you just take whatever decimal it is and just look for it on the trig sheet, say.
And look for it on the trig sheet. Yep. Or when you're doing if you're doing this, the tangent of theta is equal to the opposite over the adjacent. Adjacent. Okay. For the purposes of your calculator or for notational purposes, if you take the inverse tangent of this, it'll tell you what the angle measurement is. Okay. Ultimately, just so that you know, the reason for this is to be able to measure things indirectly. If this was a mountain you didn't want to climb, but you wanted to know how tall it was, you could measure a distance, then stand here and look up and see what angle do you have to raise your head in order to be able to see the top of the mountain. So whatever angle this is, you've measured it. Whatever distance this is, you've measured it. The one you don't know is this one over here, but you do know that the tangent of theta is equal to the opposite over the adjacent. And that means if you know this number and you know this number, you can look up this number, multiply these together, and that will tell you what the opposite side is. Okay. So the whole purpose of this is to be able to do measurements indirectly. All of this only works with right triangles.
Would that be the theta when you're looking up to see the mountain? Is that the angle of elevation?
Yes, this is you, and there's something up here to look at and something down here to look at. This is the horizon, or parallel to the horizon. When you look up, this is the angle of elevation. And when you look down, this is the angle of depression. Every right triangle has this magical relationship among its sides, and that is that a squared plus b squared is equal to c squared. That's called the Pythagorean theorem. If you know two of these sides, it's if I give you two, you can give me the third. If I give you two of these numbers, you can give me the third one. There are certain numbers that work out perfectly, like 3, 4, and 5. Those are called Pythagorean triples because you don't have to deal with radicals at all. 3 squared is 9, 4 squared is 16. Together that's 25, and that's the same as 5 squared. Or 5 squared plus 12 squared is equal to 13 squared. So 5, 12, and 13 would be a Pythagorean triple. In other words, if you know that the sides are those lengths, you know you have a right triangle. Otherwise, you got to wind up doing some work and using radicals, but we've certainly talked about that enough. Of course, all of that requires work, and in mathematics, when we can do something that doesn't require work, we consider that special. And there are two kinds of special right triangles. One of them is the isosceles right triangle. If these two sides are congruent, then these two angles are congruent by the base angle theorem. And whatever length this side is, this side has to be the same length, and this side has to be that length times the square root of 2.
Why is it the square root of 2?
Because x squared plus x squared is equal to the square root of 2x squared.
Which is x squared. You mean x squared root 2.
X squared plus x squared is equal to the square root of 2 times x, in parentheses, squared.
And
Which
that's
would make-
simplified as x.
This simplifies as 2x squared. And this simplifies as 2x
Wait, why do you
squared.
keep the 2x squared? I mean, for the second part, why do you keep the squared? Wouldn't it cancel out with the radical?
Well, when you say cancel out, I'm not exactly sure what you mean. But when we talk about the square root of 2, we're talking about the number that when you multiply it by itself will give you 2, right?
Yeah.
And squaring it is the same as multiplying it by itself. So if you have the square root of 2 times x times the square root of 2 times x, that's going to give you square root of 2, square root of 2, x, x, and that's 2x squared.
Wait, but why do you get rid of the radical? That's the only part I don't understand.
This is the number that when I multiply by itself will give me 2, right?
Yeah.
What am I doing here?
Oh, you're multiplying two of them together.
Right. So it's got to give me 2.
If you were only given, if they didn't give you the x values and they only gave you the top one, so like x squared, whatever the whole number would be, you would divide by 2. That'll be
If this number here is equal to 15,
yes.
then I would divide both sides by the square root of 2. And then I would multiply top and bottom here by the square root of 2 in order to rationalize the denominator. And I would get that. Okay? The other triangle that is special in this regard starts with the equilateral triangle. If all these sides are equal, and then I take an altitude, drop an altitude right here, that will be a right angle. This will be congruent to this because this altitude will bisect this side. So whatever this is, this will be the same. And since it started out as an equilateral triangle, that makes this 2x, and that makes this 2x. Makes these angles 60 degrees and 60 degrees. This is 60 degrees, but I'm cutting it in half, so this is 30 degrees and this is 30 degrees. And now, if I just ignore this for a little bit, and I just look at this triangle, this is called a 30, 60, 90 triangle. It's half of an equilateral triangle. The side across from 30 degrees, whatever number that is, the hypotenuse has to be twice as big because of what we just showed here. And when you do the Pythagorean theorem to find out about this side, it's the square root of 3 times x. So if you know one of these sides, you can calculate the other sides.
Can you do a problem where they give you the opposite?
Tell me which one you want to give me.
Opposite
Opposite of what?
of 60 degrees?
Okay. So what do you want it to be?
I don't care. Whatever.
Pick a number.
16.
16.
Okay.
Excellent choice. So this is equal to 16, right? If I divide both sides by the square root of 3, that's equal to x. If I multiply top and bottom by the square root of 3 in order to rationalize the denominator, I wind up with 16 square root of 3 over 3 is equal to x. So now I know what this side is. And if I double it, I get 32 square root of 3 over 3, and that will be this side. Yep.
Can you look for using Pythagorean theorem to find square root of 3x?
X squared plus the height squared is going to equal 2x squared. Okay? That's what we have right here. I have this, and I have this, and I don't have this. Agreed? So this is going to be x squared plus h squared is equal to 4x squared. H squared is equal to 3x squared, because I subtracted x squared from both sides. And when I take the square root of both sides, I get square root of 3x.
Thanks.
Now, the Pythagorean theorem only works for right triangles, and that's a bummer. It's pretty obvious that it's not going to, because if this isn't a right angle, then it's either going to be bigger or it's going to be littler, and it's going to just change all the proportions, right? Well, it turns out that there is a way to compensate for the changes of these angles, of this angle. And that is c squared is equal to a squared plus b squared minus 2 times a times b times the cosine of that angle, c, right here. So if this angle is a little bit smaller, that's compensated for here. And if it's a little bit bigger, that's compensated for here. And if it is exactly 90 degrees, well, the cosine of 90 degrees is 0. And that makes this go away. Yeah.
So I'm a little confused by what you said. So you use the same formula regardless of whether it's smaller than 90, the angle is less than 90 degrees,
Or larger than 90 degrees.
so
Yep.
you don't change the formula.
Nope. This is the formula. And it is called the law of cosines. And the truth is, you can use it for any one of these angles. Because if it's not 90 degrees, then it doesn't matter which one could have been. Okay? There is also a law of sines. Here's a right triangle. One of the things we found out, if we dropped an altitude from here and we took this and multiplied it by this, it would equal this squared. Do you remember that? We actually physically did that. We cut this and turned the two sides so that we had a square here and we had a rectangle here. Does anybody remember that at all? Yeah. The area was the same? Okay. So that's called the geometric mean. Okay. This number is the geometric mean of these two numbers. Right? We said if you have a triangle that looks like this, right? Whatever this is here, and whatever this is here, and whatever this is here, a times b is equal to h squared. Now, if you want that in another form, we could say a over h is equal to h over b. That's the same ratio. The other thing is, no matter what kind of triangle you have, the sine of a divided by the side across from it is equal to the sine of b divided by the side across from it. And that's equal to the sine of c divided by the side across from it. And that is called the law of sines.
What is the law of sines exactly used for again?
Well, the law of all of these things are used for indirect measurement. If I know this angle, and I know this angle, and I know this side, I can put them in here, and I can calculate this side.
It's used just to find missing sides.
Or missing angles, right? To measure things you can't measure directly.
How would you find an angle with it?
Well, if I knew this side, and I knew this side, and I knew this angle, then I would know that the sine of b over b would be equal to the sine of c over c, right? This number I know. These numbers I know. If I multiply both sides by c, I have c times the sine of b over b is equal to the sine of c.
Then you can just divide.
Well, can't quite divide. I have to take whatever number this is, right? I have to calculate that number and then say, let's look at the chart or use the calculator to find the inverse of whatever number that is, and that will equal the degree measure of angle C.
How do you determine when to use the log sines or cosines?
It depends on what you have. Sometimes you could use either one and it doesn't matter. Remember, the law of cosines had 4 things in it: 3 side lengths and an angle measurement. So if there is an equation with 4 variables, if you want to find one, it means you got to have 3 of them.
But you could also use, if you have like 3 things of information, you could use both.
Sometimes you can use either one, yeah.
I'm a little confused on how you would use signs. Can you show an example of log sign?
All right. Let's say this is A, B, C. Let's say this is, 20 degrees. Okay. Let's say this is 7. And let's say this is 30 degrees. And I want to know what the length of that side is. So the sine of 20 degrees divided by 7 is equal to the sine of 30 degrees divided by x. Okay. Now, I can flip both of those because that's part of the rules of proportions. Works out just as well. Now I can multiply both sides by the sine of 30 degrees. No, I'm just multiplying top and bottom. I'm multiplying both sides of this equation by the sine of 30.
So you just
So we've got a calculator. Okay, there's the sine of 30. Okay, multiply that by 7. Okay, that's 3.5. Let's get the sine of 20 degrees. Okay. And then let's divide that into 3.5. We get 10.2333, whatever that is. So this would have to be 10. And we look to see, is that a rational, does that make sense? Yeah, the side across from 20 degrees is 7. Side across from 30 degrees is going to be larger than that. That makes sense. Okay? All right. So that's pretty much what there is to know about indirect measurement of triangles.
What about the
would you leave that as 10 or 10 times 2?
Well, it depends on what you're being asked to round to. I mean, if you're doing brain surgery, then you're going to want as many decimal places as you can get. If you're answering a math quiz, 10.2 would probably be enough. The next thing we talked about was area. And we defined area as being the number of unit squares that can fit within a shape. Doesn't matter what the unit square is. This could be miles or inches or centimeters, as long as we're just using the same unit. And that is what area is. How many unit squares fit inside of a shape. Now, if your shape looks like this, it's kind of hard to tell exactly how many unit squares fit in there. You got little bits of one here, and a bigger bit of one here, and a big bit of one here. So we don't mess with that. We start with something much simpler. And that is the rectangle. if I break this into units, so this is 1, 1, 1, 1, 1, 1, 1, and then I break this into units this way, 1, 1, 1, 1. If I want to know how many squares I have, the definition of multiplication is how many squares are in here. This is 1, 2, 3, 4, 5, 6, 7 across and 4 down. So 7 times 4 is equal to however many squares are in here. And the answer to that would be 28. So if I have a rectangle that has a given side length and another given side length, I can multiply those two numbers together to find out how many squares there are inside. Another fun thing to do would be to take this chunk right here, cut it off from there, and slide it over to here. And that would make a parallelogram. Now, if this is the same length as this, then now this is B from here to here. This is still A from here to here. And area is additive. If I subtract something from here, the area of the whole thing minus this is what the area of what's left is going to be. And if I add it back over here, then it's going to go back to being the area it was in the first place. So for every parallelogram, I could always take this part and slide it back over here and make it into a rectangle again. So although it makes this side slanted, that's not really something we care about. What we care about is the size of the height and the size of the base. So here, for this parallelogram, the area of this would be A times B, just like it was for the rectangle that I started out with. And in this case, it would be 28. So it would still have the same area. The trick is not to get confused or thrown off if there's a number over here. This just doesn't fit into the calculation of the area, at least not directly. Okay. On the other hand, if I told you that this was 5, and I told you that this from here to here was 3, and then I told you, right, from here to here, and then I told you that this from here to here was 7, is that enough information to find the area of this parallelogram? Yeah, it is. What you need is this, right? You know that this base is 10. You don't need sine. You need the Pythagorean theorem. 3, 4, 5. It's a Pythagorean triple. This is going to be 4. 4 times 7 plus 3 is 40. The area of this is 40. You have to use everything you know. Whatever information you're given, you reach into your bag of tricks and you use whatever information you have. If I have a triangle that looks like this, I could take another triangle that looks exactly like this, and that will make a parallelogram. Right? Try it again. Any triangle that I have here, put an identical triangle on its side like that, and that turns this into a parallelogram. I know how to find the area of a parallelogram. Okay? I take the base, and I multiply it by the height, and I have the area of the parallelogram. But if all I want is the area of the triangle, it's 1/2 the base times the height.
Is that equal to like base times height over 2?
Mm-hmm. Yep. It's another way to write it.
Can you use the law of cosine
What? Yeah, if you the law of cosines. Yeah, the law of cosines you can use
Use with any triangle.
with any triangle. Yeah. Take a look. If I have a triangle that looks like this, any one of these sides could be the base. This could be the base, and then this would be the height. Or if I turn it sideways, this could be the base, and this could be the height. Or I could turn it this way, and this would be the base, and this would be the height right here. Okay? So it doesn't really matter. There's no one base for a triangle. The only other shape I can think of at the moment to talk about would be a trapezoid. And the beauty of the trapezoid is if you cut it in half, you have two triangles. And both triangles have the same height. They just have different bases. This would be base 1. This would be base 2. So the area of this triangle right here would be 1/2 base 2 times the height. The area of this triangle over here would be 1/2 of base 1 times the height. And if you wanted the area of the entire trapezoid, you would just add them together. You can do a couple of different fun things if you like. You could factor out an h and a 2.5 here and have b1 plus b2. Or you could say b1 plus b2 over 2 times the height. You can rewrite it any way you want, but the truth is what you're doing is cutting this in half, getting the area of that triangle, the area of that triangle, and adding them together. Okay, so if we know how to find the area of a triangle, if I make a regular polygon, and a regular polygon is one that has the same side lengths and the same angle measurements all the way around. Okay. So if I made any kind of, let's say this is a regular pentagon, I can find the center. I can make congruent triangles here. I would have 5 congruent triangles. If I wanted one that was 100 sides, I could make one triangle and then another one just like it, and another one just like it, and another one just like it, all the way around. This right here is 360 degrees. All the way around. So depending on how many sides you have, or divide 360 rather by how many sides you have. So I have 360. If I'm doing a pentagon, I'm going to divide that by 5. And that'll be 72 degrees. And that means that each one of these angles up here is 72 degrees. So it's 360 over n. And these angles are all congruent here. So whatever this angle is right here, plus 2 times that angle measurement, that has to equal 180 degrees. Is that right? Let's see. Can we simplify this a little bit?
You could divide it by 2.
Could divide it by 2. All right. That worked. I could subtract 180 from both sides. 180 over n. I would get x is equal to 90 minus 180 over n. I could actually put this together and say 90n minus 180 over n. Right? I could even do this. X is equal to n minus 2 over n times 90 degrees. Does that look familiar at all?
Yes.
It should. Because when we were trying to find this, it was twice as big as this. So that would mean that this interior angle here was going to be n minus 2 over n times 180 degrees. So there's lots of ways to go about remembering or figuring it out. Right? If you know how many sides there are, you know what each of these central angles is, you can figure out what each of these angles are. All of that's nice. So for any regular polygon, you can take one of those triangles made by the central angle here. And you could drop an altitude here and use the base times the height times 1/2 to get the area. Now you're saying to yourself, yeah, but which information do I have here? Well, it depends. If you have this angle right here and you have this side length right here, you have enough to use trigonometry to find this height right here. If you're given this length here and this length here, well, then you could use the Pythagorean theorem to get this. This is called the height of the triangle, but in terms of the polygon, this would be called the apothem, and this is called the radius. And the fact is, as soon as you have this and this, you have the information you need to get this area. And whatever the polygon is, it has n number of triangles that are exactly the same size going all the way around it. So you can multiply it by that to get the area of any regular polygon. Okay. Just to show you what I mean here. This is an octagon. Let's call this a regular octagon. 1, 2, 3, 4, 5, 6, 7, 8 sides. If I do the central angle thing to make triangles out of it, okay, I have 8 triangles that all look like this. These are congruent right here. This angle right here is going to be 360 degrees divided by 8, which is 45. Okay. Which means that depending on what side lengths I'm given, whether I'm given this, or I'm given this, or I'm given something else, I can find the height. I can use this length times this length times 1/2 to get the area of this triangle, and then multiply that by 8 to get the area of the entire octagon. If you are given the apothem, it means you're given this number right here, right? The height?
Yeah.
Well, if you also know what this number is, then it's 1/2 the base times the height, base times the height, times the number of sides. So at this point, you could probably be saying to yourself, well, that's all very nice, but area is not a standard. Why are we bothering with this?
Volume.
And the answer for that is you're going to need it for the volume, because the volume is a standard. Here's how volume works. Just like area was the number of squares you could fit in a two-dimensional shape, volume is the number of unit cubes you can fit into a three-dimensional shape. Easiest way to figure that out, for example, if you were looking at this room that we're in right now, let's say this is from the ceiling, I'm looking straight down. You notice that there are tiles on the floor, conveniently 1 foot by 1 foot tiles. If I counted how many tiles there were, I would know how many cubes it would take to cover the floor. Then, if I knew how tall the room was, how high is it to the ceiling, I would know how many layers of cubes I was going to need in order to completely fill the room. Basically, what I'm saying is, if you know the area of the base and you multiply it by the height, that will give you the number of cubes that can fit inside of a prism. A prism is a three-dimensional shape that has two congruent parallel polygons as bases, and then rectangles or parallelograms as sides connecting the vertices of the bases like this. So this would be a prism, has 1, 2, 3, 4, 5 sides. So this is a pentagon prism. But whatever prism you have, whatever the size of the base is, there's a triangle prism. If you know the area of the base and you multiply it by the height,
Wait, how is that a triangle prism if it meets at a point?
This?
Oh, okay, I
Just
see it.
imagine.
Wait, no. No, but what are the two bases?
the triangles are the bases.
Okay.
It's standard.
Okay, I see it.
Okay?
Yeah.
You have to be able to recognize that if you're talking about a shape that has only rectangles on its sides, then it's a rectangular prism. If it has any other shape at all, if it has any hope of being a prism, those two shapes have to be congruent and parallel. They have to be polygons, and they have to be connected by sides that are parallelograms. Okay? But area of the base times the height of the 3D shape, that gives you the volume. And that's also true for cylinders. So it's true for prisms and for cylinders. Area of the base times the height. So let's imagine for a moment that we have, I don't know, a cylinder like this. If we wanted to know the area, the surface area of any shape is the area of all of its sides added together. So we've got two circles, top and a bottom. We'd add them together. And then if we cut this off, like as if it were a label, and stretched it out, this would be a rectangle. This distance right here from here to here would be the circumference of the base. This would be the height. And that's how you would get, right? That's how you would get the surface area. This is called, if you're just talking about the sides and you're not talking about the bases, that's called the lateral area. Lateral.
So the surface area would be the circumference times the height plus the area of the bases.
Circumference of the base times the height times the area of the bases. Yeah, that would be all three sides added together.
So circumference times height plus the area of the bases.
Yep. Okay. The trick here is to remember that whatever shape you have, you're looking for the area of all the sides, all the surfaces. So, for example, if you had a hole in the middle of a block, that hole would have surfaces. Right? That tunnel has a surface. Right? There's an opening here, so this is not a full rectangle. It's a rectangle minus this opening, but in addition, it's got all that extra side length in there.
So you would find the surface area of the whole thing and then
Minus the lateral
Subtract.
area of the cone.
You'd subtract the two circles.
I would subtract the two circles, and then I would add the lateral area of the cylinder.
Oh, the lateral area is the area not including the bases.
Exactly. Okay. So then, what else could we do with volume? There was one other thing we did, and that was if we had a shape and we decided we were going to whittle it down to a point. So here's the point, and we're going to make this into a cone by whittling it down all the way around, just chopping some of the sides off here. Or same thing with a prism. Right. If I decided I wanted to just take as much as I could in order to get a point here, this would be called a pyramid. This would be called a cone. This would be called a pyramid. This would be called a cone. And in both cases, you would be actually whittling away, throwing away 2/3 of the original shape in order to get that cone or that pyramid. So the volume of a cone or a pyramid is equal to the area of the base, times the height of the 3D figure divided by 3. Because that's what's left after you took 2/3
how
away.
do you know it's 2/3?
We did this in class. We did. We built
Oh, yeah.
we built pyramids, and then you guys went around and you took 3 pyramids and put them together and made a prism out of it. One other part about area and volume that comes up that you really need to know. If this is 1 and this is 1, the area of this is 1. If I double the side lengths, so that now this is 1, 1, 1, 1, 1, 1, right? These side lengths now are 2, but there are 4 squares in here. And that's going to be true every time. If I triple the side lengths, so now the side lengths are 3 and 3, it's going to take 9 squares to fill it. Whatever the original side length is, if I multiply that by r, then I'll be multiplying the area by r squared.
And what's S?
S is the side length. R is the ratio. So in similar figures, right, where all of the sides are multiplied by the same ratio, if you have 2 similar figures, their areas won't have the same ratio. They'll have the ratio squared.
Times the area.
they'll have the ratio between the two areas will be r squared. Not only that, but if you decide you wanted to do 3 dimensions and you wanted to have all the side lengths equal to 3, right? You would have to have 27 squares in here
Why 27?
because you would need 9 for this for this part, right? You'd need 9 over here, and you would need 9 over here. So by increasing the length of the side by 3, I increase the area by 3 squared, and I increase the volume by 3 cubed. And that's going to be true with every ratio. The side length, the area, and the volume. The thing that I've told you from the beginning is counterintuitive. You won't think of it right away. So at this stage of the game, if you see something that says the area is this and the volume is this, or the side length is this, the ratio of the side lengths is this, what's the ratio of the areas, or vice versa, the thing that should be going through your head is, this is a trap. This is the thing I keep falling into as a trap. I need to think this through. I need to remember. The only other thing about volume, remember, is that any polygon could be the base of a cone, of a pyramid, or of a prism. So you need to know how to get the area of any regular polygon. Next thing we did after that was circles. And there are really 2 things involved in circles. What we looked at wasn't really just the circle. We looked at circles and lines. If you've got 2 lines that go through a circle, they intersect the circle at 2 points, but they intersect each other outside the circle, that's one situation. Another situation would be where you had 2 lines that intersected the circle just at 1 point, right? Here and here. These are called tangent lines. These are called secant lines. Secants, okay. Tangents. And I guess you could take one secant and one tangent. Do that. Now, when we look at these, there are 2 things that can jump out. One has to do with the angle, and the other has to do with the lengths of the segments. If you remember, we talked early on with the circle about the central angle, and we said that the central angle would be some portion of 360 degrees. And we said that this measure right here, not the length, but what we would call the measure of the arc, would be defined as the same as the measure of the angle. So these 2 are the same. We also said that if you have an inscribed angle, that means you've got 2 lines that intersect each other on the circle. If whatever arc they intercept here, the measure of this angle is going to be half of that. And it doesn't matter whether it's there or whether it's here or whether it's even all the way over here. Right? all three of these angles are going to be congruent. Here, here, here. They're all going to be half of this central angle, or half the measure of this arc. In terms of the angles here, if you take the large arc and subtract the small arc and divide it by 2, you'll get the angle measurement here. So if we call this A degrees, we call this B degrees, then this angle right here is going to be A minus B over 2 degrees. And that's going to be true when they're secants. It's going to be true when it's a secant and a tangent. It's going to be true when there are two tangents. Okay? The idea here is to look at the two arcs that are created, that are chopped off by these two lines. If the lines are intersecting on the outside of the circle, then you subtract the 2 and you divide by 2. On the other hand, these are segments of secant lines, and these are called chords. And if you have a chord that goes through the center of the circle, that's called a diameter. And half of the diameter is called the radius. That's from the center to any point on the circle. So if you have chords that intersect on the inside of the circle, this angle measurement right here, obviously these are vertical angles. They're going to be congruent. They also intercept two arcs here and here. If we call this one A degrees and we call this one B degrees over here, then this angle right here is going to be A plus B divided by 2 degrees. So if they intersect outside, you're going to subtract them. If they intersect inside, you're going to add them. This arc plus this arc divided by 2 gives you that angle. In terms of lengths, if we call this length right here A, we call this length right here B, we call this C, and call this D, these segments, A times B is going to equal C times D. AB equals CD. Okay. Now, here, for all of the situations where the lengths, where the two lines intersect outside, here is the deal with this. If you take the length of the outside segment and multiply it by the length of the entire segment, from the intersection of the lines to the far side of the intersection of the circle. Right? The outside times the whole thing. Those are going to be equal for the two sides. Okay. That's good. The outside length right here times the whole length all the way through here is going to be equal to the outside of this one times the whole length of this one. Okay. That's also true if you have a secant and a tangent. The outside of this times the whole thing is going to equal the outside of this times the whole thing, which also happens to be the outside. So if this is A, and this is B, and this is C, then a squared is going to equal b times b plus c. Even this, with the tangents, the outside times the outside is going to equal the outside times the outside. You know what? If you have two tangents, they're congruent. The very last things for circles that I want to tell you about. If you have a tangent line, the radius that intersects it at a right angle. And if you have a radius that intersects with a chord, if this is a right angle, these two sides are going to be congruent, and vice versa. If these two are congruent, this is going to be a right angle. That's only true if this is the radius. The probability of any event is equal to the number of ways that event can turn out compared to all the different ways the experiment can turn out. This is called the sample space. If it's tossing a coin, it's just heads and tails. If it's spinning a dial, it's however many different colors there are on it. If it's rolling the dice, there are 36 different ways that the dice can turn up. Okay? How many different ways can you get what you're looking for? Divided by the total number of ways that something can turn out. So, everybody had the same chart. You just had different questions. And the way this chart was set up, there were 30 brown dogs, 15 black dogs, for a total of 45 dogs altogether. Right? There were 20 cats that were brown, 25 cats that were black, for a total of 45 cats altogether. There were 50 brown animals, 40 black animals, and 90 total animals altogether. So using the table above, find the probability that the animal that you pick is a dog given that it's brown. So this is what you're given. You got one of the brown animals. There are 50 of those. 30 of them are dogs. So the answer to this question is 3 out of 5. The next question says, find the probability that you got an animal that was brown given that you got a cat. Well, these are the cats. There were 45 of those. 20 of them were brown. So 20 out of 45 becomes 4 out of 9. Find the probability that the animal you got was both a dog and black. Well, there were 90 animals altogether. 15 of them were black dogs. 15 out of 90 is the same as 1/6. Find the probability. See, and for this one, we don't even really need to look up at the chart. Given the table above, find the probability that you got a dog given that you got a cat.
0%.
Yeah, that's just not happening. Okay? If you got a cat, you can pretty well know that you did not get a dog. Now here, box contains 6 red cubes, 3 green cubes, 4 red balls, and 8 green balls. What is the probability that you got a cube given the fact that what you picked out was red? Well, there were 6 red cubes and 4 red balls. So 6 out of 10 red things, 6 red cubes. This is either 60% or 3 out of 5. Okay? What's the probability that you got a cat given that your animal was brown? Well, If your animal was brown, there were 50 of those. 20 of them were cats, 2 out of 5. Given that you got a dog, what's the probability that you got a brown one? Well, there were 45 altogether. 30 of them were brown. That's 2/3. Find the probability that you got a cat that was also black. Cat black. 25 of those out of 90. 25 out of 90, so I think that's 5 out of 18. Okay. If I tell you you got a dog, what's the probability that you got a dog?
100%.
1. If you write 100, then you should write percent after it. If it's just the probability is 1. And here we go. What's the probability that we got a ball given the fact that what we pulled out was green? Let's see, there were 3 green cubes and 8 green balls for a total of 11 green things, of which, and we're looking for balls, there were 8 of them, so it's 8 out of 11. Does anybody have any questions about any of those problems?